Today we're going to talk about arc length, the distance around a curve. If I wanted to measure the distance around the curve of y equals x squared on the interval from -1 to 2, we'd be going from point A to point B. I could certainly draw a straight line from one to the other and measure how far apart point A and point B are using a straight line. Wouldn't be that hard. We have a distance formula, which is based on the Pythagorean theorem, that tells us that the distance from any one point to the other is the square root of the sum of the squares of the x distance and the y distance. If we think of this as the x distance and the y distance over here, I'm sorry, shouldn't have squared those, just the distances. And this overall distance, yeah, we can call that d for distance. We can say that that overall distance from A to B is equal to the square root of dx squared plus dy squared, which in this case would be the square root of 3 squared plus another 3 squared, because the distance is up 3 units and over 3 units, which is the square root of 18 or 3 root 2. Fantastic, no problem. But not so fantastic, because that is not a very good estimate of the overall distance. If you wanted to get a numeric approximation for that, that would be about 4.24. But that's not a very good approximation. We can do better. How about instead of going straight from A to B, which takes us in the wrong direction, so obviously we're taking quite a shortcut there, what if instead we kind of went the long way around and still working in only straight lines, because at least they'll be easy to calculate. What if we go from A to there, follow the curve a little bit, so at least we're going in the right direction, taking pit stops along the way instead of going straight from A to B? Well, the logic is going to be the same. Each one of those distances is, using the distance formula, or think of it as the hypotenuse of a right triangle, we can think of the overall distance as just the sum of all of these little individual distances. And so for each one of these, we've got a dy and a dx, and then another dx and a dy, dx, dy. We can just think of adding up all of those individual sums. So we would take the sum of the square root of all of the dx squareds plus all of the dy squareds, which in this case would be the first right triangle, the one from from -1 to 0. The square root of, well, dx is 1, and dy is also, well, dy is technically -1. We're going to square that, so it doesn't matter. And then for the next point, we'd be going from 0, 0 to 1, 1. The distance there would be the square root of 1 squared plus 1 squared. And then the last one would be the square root of 1 squared for the dx. And then because this last distance up here is 3 units, we go from 1, 1 to 2, 4. That would be plus 3 squared. And if we do all the math here, that's root 2 plus root 2 plus root 10, or 2 root 2 plus 10, plus root 10. And again, we can use Desmos for an approximation for that. .99. Well, that's a lot bigger than 4.24. It's more than 25% bigger, so that's a big difference. And it's a much closer approximation. So yes, the approximation is better, but how can it still be improved? And I'm sure some of you are already seeing where I'm headed with this. The way we're going to make this even better is to do it more and more and more. Just like we did with integrals, we're just going to keep chopping that length up into smaller and smaller and smaller pieces. So instead of just having 3 pieces, just taking the sum of 3 pieces, and really a better way to write this would have been the sum from my first dx and my first dy up to my third because I happen to have 3 here. If I take the sum and I just keep adding more and more and more, what's going to happen to my dx's and my dy's is they're going to become infinitely small. But if I add them all up, they'll add up to the overall arc length, the overall length around the curve from A to B. And this is what it would look like. So we're going to play around with this a little bit. Some of you might have had that thought, oh, this looks familiar. This looks just like what we did when we turned the sigma notation into a definite integral, or vice versa. But there's an important difference. When we take the sum, the sigma notation, and turn it into a definite integral, it always had the setup that we were adding some function times some x distance. That, the limit as we approach an infinite number of those, that equals the definite integral of f of x dx. But we don't quite have that set up here. In fact, you can see what we're missing is that dx. Right now, we are just adding up some function. We don't really have the dx here, but we can fix that. So here's a fun little trick. We're going to play around with this square root of dx squared plus dy squared. First off, we're going to factor out a dx squared out of that sum, which is a little bit of a weird thing to say. So I'm going to do this part on the side here. I'm going to take the square root of dx squared plus dy squared, and I'm going to factor out a dx squared, still inside the radical. And that's a weird thing to say, because how do you factor dx squared out of a dy squared if there is no dx squared in that term to begin with? But this is similar to what we saw last unit with the logistics. Sometimes you can factor out a term that isn't even there, or a factor that isn't even in a term. You're just left with that term in the denominator, right? If I take dy squared and try and factor out a dx squared, I'd be left with dy squared over dx squared. Let's make that parentheses bigger. The reason to do this is because now that I have the square root of dx squared, now that it is a factor of the radicand, not a term in the radicand, I can take its square root. So I can rewrite this as the square root of 1 plus dy squared over dx squared, which I'm also going to rewrite that as dy dx squared, times dx, no longer in the square root. And now you can see how this fits the setup of the definite integral, where we wanted to see the sum function times some x distance. And so this arc length, which we call capital L, now we can see how that is the definite integral from a to b of, and if I translate that square root that I have over there, it's the square root of 1 plus dy dx, which if you want to, you can call f prime of x squared times dx. And that is the formula for arc length around a curve.